The four laws of thermodynamics are fundamental principles for understanding the relationship between energy and heat in nature. These laws play a critical role in explaining the behavior of physical systems and have significant applications in engineering, chemistry, and many scientific fields. The Zeroth law defines the thermodynamic equilibrium of systems. A system reaches equilibrium when there is no transfer of energy or matter. In this equilibrium state, the internal energy and entropy of the system remain constant over time. For example, in a thermal system, as heat is transferred from a higher temperature to a lower temperature, a point of equilibrium is established between the two sides. The equilibrium state plays an important role in many physical and chemical processes, as the stability and changes of a system depend on these equilibrium points. The first law of thermodynamics expresses the principle of conservation of energy. This law states that energy cannot be created from nothing, nor can existing energy be destroyed. The internal energy of a system changes with the heat added to or removed from the system and the work done on or by the system. For instance, when a heater converts electrical energy into heat energy, the total amount of energy remains constant during this process. This law forms the basis for energy transformations and helps in understanding concepts such as energy efficiency. The second law of thermodynamics introduces the concept of entropy. Entropy is a measure of the disorder and randomness within a system. This law states that the entropy of an isolated system tends to increase over time. In other words, entropy in nature is continuously on the rise, which implies that energy transformations always involve some losses. For example, when an ice cube melts, the orderly structure of the ice is lost, and the water molecules assume a more disordered arrangement. Consequently, energy is distributed in a way that increases the system's disorder. The third law of thermodynamics states that the entropy approaches zero as the temperature approaches absolute zero. This means that as a system's temperature gets closer to absolute zero, the atoms and molecules stop moving, and the entropy reaches its lowest level. This situation helps us understand the behavior of systems at very low temperatures. For instance, superconductors can conduct electricity with zero resistance under certain conditions. This law demonstrates how the motion of atoms and molecules is related to heat.